Hello. In today's video, we will study the concept of center of a group. Then we will also see that this center of a group is also a subgroup of G. And at the end of the video, we will see some examples. Okay. So we'll start with the definition of center of a group. Okay. We'll start with the definition. Let G be a group, then the center, which is denoted as z of G is the subset of G which consisting which consists of elements which commute with every element of G. In symbols, we can write it that Z of G, which is center of G, is actually the set which consists of those elements of G such that these elements commute with every element for all x belongs to G. Okay. Now it is clear that the center of a group G is subset of G which consists of those elements of G which commute with every element of G. Commute mean the commutative law. Okay. Now we'll see a theorem, very important theorem. This theorem says the center of a group G is a subgroup of G. To prove that this set is subgroup of G, we will consider the two-step subgroup criteria. Clearly, identity element must belongs to the center because identity element commute with every element of G because Ex is equal to X E for all X belongs to G. So this E must belongs to center. This means the center of G is a non-empty set. Now let A and B, two elements, are taken from the center of G. Since A and B are from the center, this means AX is equal to XA and BX is equal to XB for all elements of G. This is definition of center, that every element which belongs to the center commute with every element of G. So AX is equal to XA and BX is equal to XB for all X belongs to G. Now we have to show that center of G is closed under the binary operation. So we consider A, B, X. Since the associative law holds in the bigger set G, then clearly associative law hold in center. So this A into bx, and we know that this bx is actually equal to xb. So we can write it as A into xb. Also, now associative law can give us axb. And from this equality, we know that this xa is actually equal to xa. And this can be written as x into ab. And this shows that the product of elements ab also commute with every element of every element of g. This means this product ab belongs to g. Now we have to show that the inverse of every element also belongs to center of g. Sorry, here instead of g, we should write it the center of g. Okay. Now consider ax is equal to xa. Actually, we have to show that A inverse belongs to center of G, for every A belongs to center of G. Okay. We considered that AX is equal to XA because this A belongs to G. Now, if we pre and post multiply with A inverse, what we get? Using associative law, this can be written as A inverse A into X A inverse and A inverse X into A inverse. And clearly, this is identity and this is identity. So what we get is X A inverse is equal to A inverse X. And this shows that this A inverse commute with every element of G. This means this A inverse belongs to center of G. This means using two-step subgroup criteria, center of G is subgroup of G, and that is what we have to prove. Now we will see some examples. We know that the set of real numbers is grouped under addition. In this case, the center of G is the whole set itself because this group is abelian. So abelian means every element commutes with every element. So in this case, center of group is the whole group. Okay. Now another example. If we take the dihedral group for n is greater or equal to 3, then the center of this dihedral group is, we can write it as, in case of when n is even, then the center is the rotation with 0 angle and the rotation with 180 degrees. And if n is odd, then the center is only the identity element. So that's all about this video, and please subscribe the video and subscribe the channel and like the videos.